So now we go to integration. So we will do numerical integration. So we will be given n points, okay. So we have x axis, so we have x0 to xn minus 1 and values of the function at these points. So this is a common theme. Interpolation, we had n points given, xi's and yi's, and I try to fit a function. So please note that interpolation, I do not mean to find a value at a given point, any not given point which is not given, but I can give the full function, and using which you can find at any place you like. So that is the whole idea. So I am giving you a function which will go through all those points. So integration, also we have all these y's. So this is y0, y1. So some curve will go through this. So of course this curve I need to interpolate, and once I interpolate the curve, then I can find out integration. Okay, so if I have f of x, I can integrate. So well, the technology is bit in several steps, and there's many methods to integrate. So I will cover two. So this is called Newton-Cotes. Again, this is the same Newton, okay. Newton-Cotes method, and the second one will be Gaussian quadrature. In fact, so these methods are classified into two classes called simple method. Well, it's easy to see simple method and complex method. So in simple method, okay, there are some notation here. So xi's are called abscissa. Abscissa spelling. SSA, okay, abscissa. Now I am going to approximate the integral. So we have finally the formula. Whatever derivation you do, the formula for the integral. So I go from, we call this point A and point B, okay. So end points are A and B. So integral AB fx dx, this is approximated by a polynomial px dx, and this is going to be written for all the, this is a notation, okay. So the standard notation which we follow, equal to wj wi fxi. So these xi's are abscissas and these wi's are called weights. So this function is known to me, these are all yi's, and just multiply by wi, and then I get the integral. So of course the problem, our objective is to compute wi's, give you wi's. So in simple methods, xi's are linearly spaced, they are given to you, and you compute wi's. So that will be part of Newton-Cotes. But in complex method, Gaussian quadrature, xi's are not known. In fact, you get xi's so that your integral is accurate, best accurate possible. So here in this case, compute both wi and xi, so that your error is least. So this is more complicated, that's why it's called complex method, but it's really good, okay. So it gives you very accurate results. This is not so accurate, so we'll cover first which is simpler, Newton-Cotes. So idea is quite simple. So let's see, I need to get this px, which is approximation of fx. So px will apply Legendre polynomial, Legendre interpolation, which goes through all the endpoints. So we already done this. So that is why this you'll find that interpolation using which we can derive lot of numerical schemes. That's why it's called mother of, well, I won't say all, but lot of numerical schemes. So we write this as J, Lj, X, and Yj. So this function of X. Of course, it involves also Xi's, but there is no Y dependence. So once I fix X's, then this is independent of Y's. Now to get the integral, so I want I, approximate I, so integral Px dx. So my notation is slightly changing, I and j, so please don't mind, okay. So ij is running index. So the integral, so I'll put a to b endpoints. So this will act only on Lj, it can't act, well, y is a constant. So I can say yj outside some more j's integral Ljx dx a to b. Now this can be computed given xi's, given abscissas you can compute this, and so this yj, and notation is called cj with, so how many points are you using for abscissa? So minimum I need 2 points. So there is no intermediate point, it's just a and b. So the minimum will be, so let me just draw it here, a and b. So value of the functions are given here. So that's the lowest order. So it will give a linear interpolating function. So next would be, I give you 3 points. So there will be a point in between a and b. So there is a, b, and there is something in between. Linear space means it is going to be midway. So I give 3 points like this, or 4 points. So for all these points there is a, you need to give your C's, Ci's, this Cj. So I need to specify how many points are you using. So that's why there is a notation called n. So for this n is 2, for this n is 3, and we can have n equal to 4. So more points you take, more accurate that will be. Okay, so we need to integrate this. Now let's do some trivial functions. N equal to 2. So n equal to 2. What is my fx? Lj. So let's look at px. So px will be, so in fact we did this before. So x minus a, so the next point b minus a, this will be f of a, no, f of b. So if I put x equal to b, then I get f of b, and then I get x minus b, a minus b, f a. So this is a formula of Lagrange interpolation. Now, so these are LJs, 2 of them. So I need to integrate this. So that will give me 2 coefficients, which will multiply at fa and fb. So integral of this is x minus a, b minus a dx a to b. So this is straightforward, no? So 1 by b minus a, so b minus a whole squared by 2. I made one mistake, So this multiplied by b minus a. Okay, so there is a multiplication of b minus a. So C's are, the dependence on b minus a is less on C's. So there is a b minus a factor. So this is b minus a by 2. Implies what is C corresponding to this? Half. So C corresponding to point B is half. Similarly, you can compute, this is just algebra, C corresponding to A is also half for n equal to 2. So what is the answer for integral formula for n equal to 2? So it is b minus a half y a plus half y. Okay. So this, what is it called? You might have heard this trapezoid rule. In fact, the area, this is the area. So this is called trapezoid rule. We can also do for n equal to 3, that is a Simpson rule. So n equal to 3 has 3 coefficients and n equal to 4 has 4 coefficients and so on. Okay. So I am going to run the code, actually I will use SymPy, well I hope you want to learn it. So symbolic manipulation, I can do integral exactly. It won't be numerical integration, but this integration can be done exactly because a, b are symbols and I will get half, exact half. Okay, so I will show you how to use SymPy. But let's, before going into that, so this is a formula for arbitrary n. Okay, this is called Newton-Cotes method. So your objective is to compute this. Now what is error? So we should also be able to find out what the error is, formula for the error. So how do I estimate error? So I am going to erase this part. So table I will show you. So once I start the computer I will show you the table where C's are nicely tabulated. You don't need to compute, you just take from the table. Well, you compute once, I would say that you should compute once, but then after that take from the table. So how do I estimate error? So we already done the error for Legendre polynomial. So remember the error? Yes. This is analytically doable. Well, which order you want? I mean, the computer will do for 50th orders. In fact, computer will do it. It will take longer time. It can do 100th polynomial. Symbolic. So I will show you how to do it. Okay, that is not numerical. That is like Mathematica. It's symbolic manipulation. Actually, no, look, here polynomials can be integrated. So these are polynomials. So polynomials can be integrated analytically. These are polynomials, so integration is possible. Okay, so error I estimate by what is the error in the Legendre polynomial itself. So what is fx minus px, which is error? E of x, we said is 1 over n factorial fn zeta. Zeta lies between a and b. We don't know what zeta is, but zeta is a point in between. Product x minus xi's. I goes from 0 to n minus 1. Okay, so this is the error in the function. We don't know zeta, but zeta lies in between. Okay, so how do I estimate the error? So I wanted fx dx, but I computed px dx. So error is basically integral of ex dx. So error is integral a to b ex dx. So this is a number. We don't know zeta, but we can make an estimate what is this number, upper bound on it. But this is doable. This integral again computer will do it. So I can do 1 over n factorial f n zeta and integral of this so there is error. but there is a little bit of catch. When once I do it, I have done this integral. So if there are only 2 points, then error is finite, because this function will be, so what is this function will be, for 2 points is product of, for n equal to 2, let us write n equal to 2, my function with this guy will be x minus a, x minus b. So this 0 at both ends, but it is quadratic in between. So this function looks like that. So area under curve is finite. Okay, so that is this non-zero value. But for n equal to 3, you get, so in fact this is the midpoint. So x minus a, x minus mid, x minus b. This will have behavior like this, and it turns out it becomes 0, which is good actually. Why is it good? Yeah, so my error at that order is 0, but I can't say my error is 0. I have to go to higher order. So error is higher order. So just to, so I will give you the table, okay. So this will, the computer will do all the computation. For this, error is of the order h cube, and h is b minus a, h cube. So you can just do the algebra, it's h cube, but for this error is h5, not h4, because h4 is 0, it goes higher order. So it gives you much better accuracy. So you choose n odd points. So the one, the first, so well, I will approximate, if this is giving you 0, well I say, well, the fx you have to keep the polynomial of the next order in that computation, and then that I will do is, so I multiply this by taking a point outside. I take a point outside and make a polynomial go through this, but integral only from here to here. So Ex is integrated from a to b, but my polynomial is a higher order polynomial, and that gives you non-zero error. So this error, I mean I am not going to do the algebra here, but error is less for n odd. Okay. So now let's, so is that clear? The idea is clear for all of you. Now I will show you 2 codes, one how to compute this CIs, and second just do Newton-Cotes by various orders. So which one should I do first? CI. Okay. Now actually let's do the other one, because CI has some new concepts. So Newton-Cotes, given CIs, I will show you how to compute. I mean this is straightforward, but just the code, you should go through the code and how to compute the error. Okay, so before we go there, I will just show you the table. So this is a table given in any book. Okay. So how do I get the coefficients? So coefficient is obtained by, so divide each of these numbers by n, capital N. So it's going to be 1 by 2, 1 by 2 for n equal to 2, number of points. If number of points is 3, then it's going to be 1 by 6, 4 by 6, 1 by 6 is computed. In fact, I will show you how to compute them by SymPy. So for n equal to 4, the leftmost point is 1 by 8, the 2 midpoints are 3 by 8, 3 by 8 each, and the last point is 1 by 8. Okay, this is symmetric, you see that is symmetric. So these are the table given to you, so you don't need to compute from scratch. And what's the error? So is that clear? So this is up to 7th order. You can compute higher order, I mean this will be not a problem. So error for 2 points, error is h cube, and the zeta, f3 zeta, third derivative of zeta, but this will always put a bound, lower and upper bound. I did that for exponential. So this is always, we don't compute zeta, I mean that's insane, you don't want to compute zeta, and so it's order h cube. P3 is order h5, I am not sure you can see this order h5, so it jumped by 2. So 3 I should expect at 4, but 4th order is 0. You go order higher, So h is small, supposed to be h is supposed to be small, so this is more accurate. P4 gives you h5, so P3 and P4 have same accuracy in terms of h. Free factor is different, but same accuracy. P5 is again h7 and P6 is again h7. Okay, so these are formulas we can also compute using SymPy. Okay, like the factors 112, 190 is all comes. Okay, so let's see the code. This is coefficient. All right, so this is computing at different orders. So this is slightly tiny fonts. So Newton-Cotes, the number of points, the function, I can pass a function as argument, which I am not sure, you may not have done it. You can pass a function as an argument to in Python. So we will define f, like f is defined here, is sin x. Now this is my definition. This is a lower point and this is the minimum x and this max x. Okay. So for second order this is just AB. For third order I have to insert a intermediate point. So h is half of b minus a by 2. Well, half of b minus a. So so this is the formula for 2 points, right? This trapezoid rule. For 3 points, this is again coming straight from the table. 1/6 of the first point, 4/6 of the second point, and 1/6 of the, sorry, not 4/6. Yeah, 4/6. Third is 1/6 again, and multiply by b minus a always. So these are all multiplied by b minus a, and these are all taken from the table. Is it clear how to write the formula? So every point you multiply ci's and multiply by b minus a at the end. So if I so this will give me a function, give me the endpoints, and give me the number of points you want to use. So you give me a and b, you don't give me the intermediate point. I will compute it. It's linearly spaced. Okay, so if we run it, so this part is running the code. So max order is 6, so I go up to 6th order. I integrate it, so and put the value in intake. An error is here. From j going to 2 to 6 range, actually it will go up to 2 to 5 in fact, right? It won't, range will take up to only 5. Range is last minus 1. So Newton-Cotes, I invoke the formula, the function, and error is computed as this. It's absolute, you just take the absolute of this, and I print it. I also plot it. So so remember, I need at least 2 points. So I should not plot for point 1 or point 0 because they are all zeros, and they are plotted in log scale because error is falling kind of exponentially. So I am putting log scale, and this is 2 to max order. So it will go to max order minus 1, right? Is range, I am using range, and this error up to this again is max order minus 1. The last point is max order minus 1. Okay, these are standard. You understand where is x order minus 1, right? So if I say array of size array 5, then the last one has index 4. So that's the last index is 4. Okay, so I put the label. So if you just run this, so shall I run it, or I can show you the figure plot. So okay, let's run it. It will give 2 plots, but first let me just run this. Oh. So it's giving you, okay, this is a, no actually this is figure, they are running two of them, so this is error. So this for n equal to 2, error is of the 0.1. So this sine function 0 to pi by 2. Answer is 1, right? Integral sin x dx. And the error is 0.1, which is 10%, which is significant. But then it has come down to just taking 3 points. Error is it is 10 minus 3, so which is 0.1%. And 3 to 4, error didn't decrease much. So every odd point, the error decreases rapidly. So you should use odd number of points. And at 5, error again decreases. 6, it won't be decrease much, and at 7, it will decrease again. Okay, so we can compute error. Now, suppose I have a function a and b are far apart. A and b are not close by, they are far apart. So my function may be reasonably like this. If you use trapezoid rule, this is bad, right? You should not use. If you use higher order, it may capture intermediate. Well, I mean, it may capture intermediate, but this actually you should do. What should I do here? I should not use just 2 points. The idea is to make further divisions, and each of this part I apply Newton-Cotes. So that's the idea. So you should apply Newton-Cotes at each of the each of the small slices. So I made many slices. So I have one example where I can just apply trapezoid rule for with many slices. So suppose we have m slices. Okay, so I am going to apply only trapezoid rule. This is simple to illustrate. You can also use the higher order. Of course, I am assuming that a function can be computed at all these points. Okay, is that clear? So I am going to do trapezoid here, trapezoid here, trapezoid here, trapezoid here. So this is point A and B, but I have intermediate points. So actually, if you may call, this is B, then this is again AB, like this. This is what I am trying to do. So this is x0 and this is xn minus 1. So trapezoid rule will give you what? The first integral will give you x0 plus x1 by 2. Not function, not x0, half multiplied by this h, not b minus a. So h. Then same thing I will get for fx1, I am going to make a shorthand, fx2, like this. So it's a sum of trapezoidal sums of each segment, each slice. But if you see, fx1 can be added from here and here. So all the intermediate points you can add half plus half. So this involves how many multiplication and addition? It involves 2 addition for each slice. I can decrease the order. I can write this as sum fxi's. So sum over all, because all of them are 1, because there is a half contribution from the left and half contribution from the right, but at the end points factor is half, right? So what I should do, I just sum it up, minus half at f0 plus fn minus 1. This is cheaper, right? I mean, I don't have to do n sums, I just, sorry, 2 n sums, I just do n sums and subtract one number here. Okay? So these kind of tricks one can use and one should use. So that is a part shown here as well. So if this is quite common, that you do trapezoid rule for many slices or Simpson rule for many slices. So this integration part is given here. So Newton-Cotes 2, but for 2, but I do for n points. So this is, so I have to compute h, which is b minus a. So there are n minus 1 slices, and then I do this sum. So I'm just doing this sum, and finally subtract half of the endpoints. So this will give me the answer for different h. So this is what is done here. Yeah, max number of points is 10, then this sum is straightforward. Okay, so I get for different h. So first time h is big, which is pi by 2. The next time is h is pi by 2, pi by 4, then pi by 8. Oh, no, not pi by 8, pi by 6. So I just keep dividing, 1 by 2, 1 by 3, 1 by 4. So that was the other plot which we saw. So question is, how does error decrease with h? I am making small and small slices. So we know the answer, no? I told you the answer. How does error decrease with h? Who said h cube? Error decreases h cube, and so this is h cube. So this for h which is largest h, this one, then I decrease h by 2, this is h by 3, h by 4, h by 5, like this, and this line is cube, h cube. So I am going to finer and finer h, and my error is decreasing, 10 power minus, well, I mean, something like, so you know how to read this off? What is this value, this value? You see the ticks? So what is the value, tell me? This value is how much? Y-axis? 0.001. What does this tick correspond to? This one, 0.002. Okay, so you should know how to read the log scale. Next is 0.003. This 0.004. They are not linearly spaced because it's log scale. Okay, and when you're plotting them, so this is 0.2, 0.3, 0.4, like this. Okay, so this is h cube. So it is going like h cube, you can say. Okay, so I have 10 minutes to briefly introduce the SimPy. So SimPy, let's just do 1 or 2 functions. So I'll just do one. This will be quick, okay? But I have 10 minutes. So first import SimPy, or from SimPy import SYM for symbolic. Now here I have to define which are symbols and which are numbers. Well, you don't define which are numbers. Numbers are already known. Symbols you have to define which are symbols, and is defined as, so let's say I want to use x as a symbol. So say x equal to symbols, and what are you going to use in your code, in your program? So I'm going to say x, I'm going to use x itself, but x will not be evil weighted. Computer knows that it is a symbol. So I put in single quotes. So this tells that x is a symbol. Okay, so enter. Actually no, let's do one thing. Because I have to say SimPy dot symbols, no, that's what I, okay. So I want to avoid that. So it's, so x is symbol. Now you want to, sorry, Star means all. Okay. So you want to integrate. So actually SymPy has a very good documentation. You can just download the PDF file. So SymPy documentation, if you say, you'll get the full documentation. But I want to do integration. So integrate. So integrate x. So you know, let's say x squared. So I want to integrate with x itself. So it will do the symbolic integration x cubed by 3. Okay. So it just, so this is, it assumes that it is x symbol and it will do it. I want to do within a bound. So if you want to do within a bound, so you say x lower bound and upper bound, it will give exact number. It is not going to do numerical integration, it gives just exact integration and 1/3. Okay. So we will use this feature to do our computation of CIs. So is it clear? I mean, this is quite simple. You just have to specify the symbols and you just have to do it. And that's, so it can do a lot of stuff. I mean, this is really fancy. You can do differentiate, you can do vector calculus, derivative, gradient, all of it. Okay. Where is my? Okay, so you have to see this code quite carefully. So okay, so first start, I want to declare what are my symbols. So I have quite a few symbols, so you can do in one shot. So symbol within argument, you have to put within a small bracket argument, small brackets. So x, a, b and h, these are my symbols. So n is 3, so I am just choosing 3 points. So my h will be b minus a by n minus 1. So this n is an integer, so the computer knows that part. And I am going to create x arrays which will give me the coordinates of the abscissors. X array contains abscissors. So what are they? I just do in a loop. So a plus ih, straightforward, right? So it will be containing symbols, will be a plus h, a plus 2h, a plus n minus 1h, symbols. Now this is the loop. If you read my code about Legendre polynomial, it is exactly copied from there. So copy paste, okay, there is no shame in copy paste, just copy paste. So n is size of the array. So coefficient, I am going to create, so I will basically club together in array. So coefficient is an array, so you go in a loop. So I have to, how many elements are there? The coefficients are there. So I have 0 to n minus 1, n of them. And so numerator, this part is common from our earlier code. So so j not equal to y, so this is that Lj, this is Lj, I get Lj, symbolic. Then I just integrate it from a to b. Since I had to factor b minus a, so I have to remember there is a b minus a factor. I told that b minus a is outside, so I have to divide by b minus a, and you would use simplify. If you don't simplify, it's a big expression, and computer also compacts it. It does intelligently compacts it, and it gives a number, and I append it to in the loop. So after all this computation, I will get all the CIs for given n. I can also compute error. So for this factor is x minus xi for all i's. But recall I said for even n that will work, for odd n I have to use a point after b. So this is that condition. So if it is odd or even, you have to do it separately. Okay. So this part I am just multiplying by one extra factor. So this works. So is that clear to everybody? So just have to do symbol, and only thing is difference in our earlier coding of Python is this is symbol, and I had to do integration here like this. So let's run it. We have 3 minutes. Is that okay? So I'll share the code. You just have a look and study it. So run Newton-Cotes. So I have to run this function. So let's see. So it has defined the function. So I need to run it. So you can see what is x. X is a symbol. What is h? H is, so I am using n equal to 3. N equal to 3. Yeah. So n is 3. So yeah, 3 minus 2. So that is h.
So what does the function simplify?
Simplify. So without simplification, the function is long one. It has a cube, b cube, all that. So it will try to. So what is a minus b squared? So a squared plus b squared minus 2ab. So it will compact it. It will divide it. So it will do some more simplification. So that is h for 3 points. So I basically need the midpoint, right? When this is the midpoint, so this is h. Okay. So I need the answer. So Newton-Cotes coefficients. So it will return what? It returns both coefficients as well as error factor. So X array is already there, so you just need to call X array is this for 3 points. So Newton-Cotes. Okay, so these are the answers. So my coefficients are 1/6, 2/3, which is 4/6 and 1/6, and error is -1/90. So I divide by already h5. I divide by h5. You look at the error part, so there is a division. Okay, so it works. So you look at the table, this is exactly same number. You can increase n or decrease n. Let's decrease n. And error is -1/12 h cube. So I need to run again. So this is my answer. Okay, so half coefficient, and error is -1/12 h cube. So you can put n equal to 4. So it will work for all of them. So you just can create this. Okay. So you get it. Okay. So you play around with this. Simpa is slightly. I mean, you have to just be used to it. Okay. Thanks.